All right, moving into another lesson, and we'll just title this one "The Central Limit Theorem and Sampling Distributions." Um, I think this is going to be a slightly more complicated concept, so I think it's extremely important that you pump the brakes, slow down, watch this video very, very, very carefully, and get started off on the right foot. Because what I'm going to do, I'm going to embed the new content, the new stuff I want you to be able to do in stuff we should already be able to do. And I believe if you can make the transition, you're going to have a lot more success in this lesson. So let's think about what we did previously with normal distribution. So this statement right here would just say that IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. First number is the mean, the second number is the standard deviation. The type of problem that we've looked at previously is like what percentage of IQs are greater than 118? Well, we know we can do that very easily using StatCrunch. So if we come over here and grab under Stat, go to Calculator, come down to Normal Distribution because of that right there, and make it happen. Our mean is 100. Our standard deviation is 15. We need greater than, because that's what the problem says, greater than 118. Put in 118, compute, so our answer is 0.1151. Okay, now shifting into central limit theorem and sampling distributions, we have to understand that this problem, what percentage of IQs are greater, actually it should be is greater, percent, right? Percentage is greater than 118. This problem is equivalent to asking the following. If a person is selected at random, what is the probability that their IQ exceeds 118? And another way in shorthand of doing that would just be, capital P and then the variable IQ, and that could be X in general, but in this case we have a specific variable, IQ greater than 118. Those problems are the same. All three of these problems require what I've done over here to the left in StatCrunch to work it successfully. Now, again, just trying to build the foundation where all this stuff doesn't hit you like kind of all at once. I want to transition into this slowly because this is typically content that students struggle with. Now, there's a lot going on in this chart right here, this drawing that I've given you, but it's an extremely important one that we need to tattoo to the memory and make sure that we understand it. First of all, this class, statistics in general, pertains to the relationship, the the dynamics between a sample and a population. Now, depending on which way we go, let's say this bottom, if we start with our population, so in other words, start here, that's what we know. And we want to determine the likelihood of getting a sample from that population where the sample is unknown because we don't know what we're going to get. This is going to be drawn at random. Then we can use the laws of probability to determine the likelihood of getting that sample. For example, let's say that my population is a standard deck of cards, aces, kings, queens, clubs, heart, all that, 52 cards. I know what I'm drawing from. So I can determine using probability the likelihood of getting, for example, uh, a king of hearts, right? Which would be unknown. I don't know what I'm going to get when I go in and draw a card at random from a standard deck of cards of 52 cards. I don't know what I'm going to get. That's why I put unknown here. But again, I can determine the probability of getting a particular sample from this population. Again, known, same thing we just did. Population is IQ scores. Um, mean 100, standard deviation 15. I don't know what the IQ of the person is going to be that I draw at random, but I can determine the probability that that IQ is greater than 118, which I just did, right? That's all in the realm of probability. Now, when I start moving the other way, where my sample is known, start here, and I'm trying to make a statement about a population value that is unknown, then that is what we do in inferential statistics. Most statistics classes, this one included, are divided into three components: descriptive statistics, probability, and inference. Descriptive statistics is constructing histograms and box plots and pie charts and finding means and medians and standard deviations and frequencies and percentages and different things. The probability is determining the likelihood of something from a population that we know. And then inference is what I'll teach you in lessons, well, the remaining lessons, some of the remaining lessons. All right, so now why population known? Why does this have to be known? Well, imagine me telling you that your population is 5 cards, right? But I don't tell you what they are. What's the probability of getting an ace? Well, you can't tell me because you don't know the cards from which I am drawing, right? So the population must be known to determine the probability of getting something from it. So what do we know now? Let's pump the brakes a little bit. First of all, we know how to find the probability given one person. If, again, circling back to the question before, we select a person at random. What is the probability that their IQ is greater than 118? Well, this right here answers that question for us. Would we feel comfortable? Now, again, let me pump the brakes a little bit. This diagram forms a cycle. All of this is interrelated. Everything that we do up here depends on what we learn down here. All right, again, everything we do in inference depends on probability. One of the key things, one of the key elements, one of the key measurements in inference is called a p-value. What do you think the p-value stands for? It stands for a probability. So everything we do up here, these decisions that we make in inference, these estimates that we make in inference, are related to probability. Okay, so would we feel comfortable conducting a study on one person? I would not. Let's say that I want to estimate the mean IQ for all left-handed people. All right. And we'll define left-handed as being you write the majority of the time using your left hand. Okay? Well, I don't know the answer to that. So my population is unknown, but I could go out and take a sample and collect my sample and make an inference. Would I feel comfortable doing that study on one person? Right? So I choose a person who is left-handed, I give them an IQ test. Their IQ is 112. I just generalize it. Every single person that's left-handed has an IQ of 112. That would be goofy statistics. I wouldn't want to do that. I'd want to collect a sample where I have more than one person, and I'd want to use it to make an inference about the unknown value in our population. So that's the goal here, to study probability for samples. So we've got to study the probability. We've got to extend what we know down here from calculating probabilities for one person at a time, because it wouldn't make sense. Let me get that a little clearer so you don't lose your eyesight. When I put my hand in there, it messes it up. One person at a time to make inference. We want to find the probability of a sample, 2 people, 5 people, 50 people, 100 people, 1,000 people. What's the probability look like when we start taking samples at more than one at a time, so we can be prepared to use that in inference? All right, that was kind of lengthy, kind of wordy. I apologize, but it's just I need you to have a solid foundation uh, uh, in the motivation for studying sampling distributions and central limit theorem before I move on. All right, here's what happens. We start out with a population, and for right now, I want to study means. So let's, I've got some stuff written here on page 3. Just as a reminder, a little review refresher. Remember the notation. X bar is our sample mean, SX is our sample standard deviation, mu is our population mean, and sigma is our population standard deviation. So our overarching question here, how do samples behave? What happens when I take multiple samples from a population? What do they do? How do they react? So let's simulate that. So I have this population where the mean and the standard deviation are known. If, sorry about that. If it works better for you, the mean is 100, standard deviation is 15. All right, that's what it is. Now, is this population normally distributed? Well, it either is or it isn't. Daggone it. If it is, our sample size only needs to be 2 or larger. If it's not normally distributed, our sample size needs to be, depending on the reference, I've seen 25 listed, I've seen 30. So just kind of keep the 25 or 30 target on your radar if you don't start out with a normally distributed population. How do you know this information? It'll be given in the problem. So again, you start out with a question. It says you're drawing samples from a population that is not normally distributed. Then for you to be able to proceed, you have to have a sample size of 30, 25, or 30. If the population is defined to be normally distributed, then everything I'm getting ready to teach you, called the central limit theorem, only needs sample size of 2 or larger. All right, so set n. So we don't let n vary. So based on, again, the distribution, it's going to be 2, 25, 30, 100, whatever. Let's just say, for the sake of this illustration, that we set n to be 100. It doesn't have to be 100. It could be 88. It could be 1,012. It could be whatever. We just set it and we hold it constant. We don't let n vary after we set it. All right? And this would work out nice because it doesn't matter if we have a normal distribution or not. 100 is bigger than 2, and 100 is bigger than 25 or 30. So the distribution shape of this population would be irrelevant because I've set my sample size high enough. Now, here's where the fun starts. Imagine diving in your population and pulling out 100 people, and you measure each of these 100 people. You get their, whatever the value is. So as we're doing IQs, we take their IQs. So we have 100 IQs. We add all the 100 IQs up. We divide by 100. We get a sample mean for the first collection of 100 people. That's all that little 1 means right there. It's just a subscript. It's just to communicate to you that this is the sample mean for the first 100 people. Close your eyes, throw those 100 people back in the mix. So we're doing what's called probability with replacement. Okay. And we pull out 100 people at random again. We give them all an IQ test. We get their IQs. We divide by 100. We get a sample mean for the second group of 100 people. We do that again. We do that again. We do this forever. All right. Be a long homework assignment, right? Well, it isn't. We're talking about these things in theory. We don't actually collect them. We just know that these sample means exist. I could forever and ever and ever and ever pull sample means from this population, size 100, and I would exhaust all the possible outcomes. That's all we're saying here. These are all the possible outcomes. Well, we call this the distribution of sample means X bar. So again, the distribution of sample means X bar, or just the distribution of sample means. The central limit theorem tells us three things. So that's central limit theorem. The central limit theorem tells us three things about all of these numbers. The first thing it tells us is the shape is going to be normally distributed. Yep, that's exactly what I said. We can start out with a non-normal distribution. We can start out with a severely skewed distribution. And as long as my samples are, sample size is set at 25 or 30, which it would be at 100, the distribution of these sample means, if I put these means in a calculator and create a histogram, my distribution is going to be normally distributed. And it gets more, at least closer to a normal distribution as the sample size gets bigger. So 100 would almost guarantee the result to be normally distributed. The next thing it tells me is that the population mean of these X bars. So if I can take this number plus this number plus this number plus this number, all these numbers, add them up and divide by however many I have, the population mean of those values is going to be equal to the original population mean that I started with way back here. The standard deviation of those values, we expect variation, right? We don't expect all these samples to be the same. So the standard deviation of all these values right here, given by this notation, which by the way we call the standard error. So something new that we add to our terminology. Up here, if we're taking values out of our population one at a time, then the standard deviation is just sigma. But once we start taking the standard deviation of the sample means, where these things are created on more than one value at a time, we get what's called a standard error. And this is found by just taking the square sigma, again, right back here, over the square root of n. Now, a lot of students at this level just don't think good in abstract. So let's do an example with real numbers. We start with a population. And let's just say our population is all IQ scores. All right, so normally distributed. Mean equal 100. Standard deviation equal 15. All right, normal distribution or not? Well, it is, right? So for all this to work, all I need is a sample size greater than 2, or 2 or larger. Because think about it, to have a sample mean, I need at least 2 people. One score is just a score. To get a mean, I have to have at least 2 so I can add them together and divide by 2 or 3 or 7 or whatever it may be. Well, I don't know. I'm going to set n equal 37, just for the heck of it. So what I do, I go in my population of IQ scores, I pull out 37 people, I give them the IQ test, I add up all their IQs, I divide by 37, and I get the first sample mean, and let's say, just for the heck of it, that that's 118.2, whatever it may be. I put those people back in the mix, I pull out 37 more people, I get a sample mean for those 37 people, and this is 97.4 or whatever it may be. I don't know what these are. It doesn't matter. I do this forever. The thing that I'm trying to do at this stage is to let you know that these sample means are real numbers. These are numbers that we actually add up 37 people IQs and divide by 37, and we get these values. What are all these numbers called? It's called the distribution of sample means. What do I know about all these numbers? They're normally distributed. Why is that important? Well, that's important because I got a calculator key over here that works those problems for me. If I don't know that it's normally distributed, I don't know which one of these that I have to use to calculate the value of a probability, right? I know that the mean value, if I take 118.2 plus 97.4 plus whatever, plus whatever, plus whatever, and divide by, how many I have, that value is going to be the same as the mean I started with back here. And I know that the standard deviation is going to be what? Sigma over the square root of n. Sigma, I started with up here is 15. The n that I set was 37. Let me grab my calculator real quick and see what that turns out to be. So I get 2.466, let's call it. Of course, the further you round out here, when you use it to make a calculation later, it gives you a more accurate answer. All right, now let's talk about the problems that I want you to be able to do. A person is selected at random. What is the probability that their IQ is less than 108? Now, what's tempting to do? It's tempting to say, well, I've learned this new tool. I have this new bag of tricks called the central limit theorem, then I should apply it. But no, you don't throw out the tools that you already have when they don't apply. This is still a problem from the previous lesson. It doesn't apply to the new stuff. Mean 100, standard deviation 15. I need less than 108. The answer is 0.7031. All right, new question. 12 people think n equal 12 are selected at random. What is the probability that their mean IQ is less than 108? Now, what's the difference in this problem and this problem? Well, up here, we're taking a person one at a time. A person is selected at random. Down here, we're taking 12 people. So up here, we're just looking at the probability of their IQ, that 108 for them only. Down here, we're taking 12 people, and we're looking at the sample mean for these 12 people. So what's the probability that their mean IQ is less than 108? The only thing you have to do different for working this problem and this problem, because again, what's the central limit theorem tell us? Means 100. Standard deviation changes. The only thing you have to do is change your standard deviation. It's no longer 15. It's 15 divided by the square root of n, which for this problem that we are working the sample size is equal to 12. All right, so I still need that, and this actually should be X bar, but we just have to understand the context of the problem we're working, all right? Less than 108. And the answer is 0.9677. People complicate these problems because there's a lot going on, but to put these things into action and actually apply them and actually work the problems and get the correct answer, which is always cool. The only thing we need to do is change the standard deviation. You just cannot forget to or divide these population standard deviation by the square root of the sample size. Now, let's pump the brakes a little bit and say, can we even work this problem? Because if we had a skewed distribution, 12 wouldn't be enough, would it? We need 25 or 30. But since this is a normal distribution, IQs are normally distributed, we've defined that previously, then 12 is big enough because we have, it just needs to be 2 or larger. All right, so I'm going to end there. I'm going to get a collection of questions from my stat lab, going to be kind of similar to things you're going to work for your homework assignment and on your exams, and I'll work those, and hopefully this will become a little clearer. All right, that's all I got. Take care.